Hello everyone. In this video lesson, let us learn how the computer programs work and what do people mean when they say computer understands only ones and zeros. So in order to understand that, we need to understand the components of a computer. Computers such as your laptop, your cell phones, embedded systems like smart TV, weather monitoring systems and stuff like that have basic components. So they are, one is your CPU, which is central processing unit, which does all the calculations that is required. Second is your RAM, or random access memory, where the instructions and the data is stored. And additionally, you can have a secondary memory, which is sometimes a hard disk or a pen drive or whatever. So you have a secondary memory to store the data so that when you switch off the computer, the data is persistent. In RAM, since it is made up of capacitors, it cannot hold data for long time. So as long as the computer is switched on, the RAM can have its voltages stored inside the capacitors. And these signals are read by CPU. So let us understand how the CPU interprets the data that is read from RAM. You might have heard a million times that a CPU understands only ones and zeros. So what does it mean? So it just means that CPU is a electrical chip, and that means the chip can read only electrical signals. It can read ones and zeros, which is nothing but the voltages or the electrical signals. That means 1 might mean high voltage, 0 might mean relatively low voltage. So CPU, you might have seen the CPU. It has some sorts of pins. If you open up your motherboard, you can see that. And then these pins are capable of reading or getting the electrical signals, and these signals are nothing but ones and zeros. This is what people mean when they say computer understands only ones and zeros. It's actually electrical signals. So CPU has limited memory, and its job is only to calculate trivial instructions such as add, move, load, and such things. We'll see it in a while. So the RAM is the one who supplies this set of signals or this set of instructions and the data. The CPU can read the data from RAM via addressing system. So if you could take a RAM, it has an list of addresses. That means if you have a CPU of 4 bits, so it can address 2 power 4 addresses from the RAM. Okay. That means RAM can have only 16 locations. 1, 2, 3, 4, up to 16. But if the CPU is 32 bits, it can have 2 power 32. It can address 2 power 32 memory locations from the RAM. That means it can support RAM of 4 GB. It is roughly 4 GB. So let us try to understand how the data is interpreted by CPU. Let me clear this. So when it tries to read a bit stream or few signals from the RAM from a location in RAM, and here we have the CPU. This is the RAM. So when it tries to read the data from the RAM, CPU stores this data in something called as registers. They are memory locations, but they are of very limited size. So they take that in and try to interpret this bit stream or the signals that they are getting. So this bit stream might be interpreted something like this part is of an opcode. Opcode is nothing but what is the operation that you need to do. Say for example, it could be add, and this bits could be the data which this opcode operates on. So let me have, and this could be y. So the instructions that are read from the RAM might map roughly to this. So it can have an opcode and it has data that can operate. So CPU disintegrates, or CPU interprets this part by part. One is opcode and next is the data that which operates. So that means each of the CPUs have their own opcodes, because CPUs are manufactured by a lot of companies such as Intel, Motorola, Qualcomm, and a lot of other companies, AMD, and there are so many companies. So these opcodes are very specific to the version and the hardware that the chip provider uh, makes. So let us see what is the problem. So if you have to write a program to tell the CPU to do some operation, you have to write code in binary numbers, something like this, and you can only write this only if you understand how the CPU tries to interpret this data into different parts. And you must memorize or look up all the opcodes to do the operations. Say for example, if you want to calculate sum of two numbers, you must know what is the opcode for add, and you must know the binary representation of those numbers, x and y, say for example, are 2 and 3, and then you must pass the opcode and the binary values for the data that you are sending to CPU. So until this it's only we are interacting directly with the hardware. That means we are sending the signals directly to the CPU. The problem is that for humans it is insanely difficult to remember all the opcodes and the sequence of the data that you are sending. So in order to automate this, what people came up was something called as assemblers. So assemblers can take in some sort of basic instructions, something like add x, y, load z, and jump to certain line number or instruction, jump y, not y, y is already used, jump to a certain routine, routine R, something like this. So this code is slightly better than writing binary codes or binary programs and sending it to CPU. So this is the advent of assembly level languages. We are essentially automating the binary representation to slightly human readable format. But you must notice that these instructions are still hardbound to the hardware. That means each chip vendor, when they produce chips, they provide you with a manual saying that these are the set of instructions and this is how you need to try to interact with the CPU. So this poses another challenge. That challenge is, for every chip that is produced out in the market, programmers have to read the big thick manual and then understand how it interacts with the hardware, and they have to write the program. So this is how people used to program for a long time, and even today there are some systems where uh, there are no operating systems possible to be installed on certain devices because of the memory constraint, and people can write assembly level code, and then they try to convert to the uh, binary code, and then it is able to read that code. Now the question is it possible to remember all the chips manual, or all the chips instructions? It is not possible. So that is why there was a new idea to automate the assembly level languages to something called as high level languages. So examples are Fortran, Basic, and C, and COBOL. A lot of languages you can look up online. So these languages, essentially what they did was they tried to convert slightly human readable format, such as maybe something like hash include .stdio.h, int main, something like this, and return something. So this is much more readable than the assembly level language that is very specific to hardware. So now we have automated at the second level. That means first level we automated the binary code to assembly level language, and then the second level automation was to try to generate the assembly level code using high level languages. So now the problem is still there. The problem is that there are so many chips that are coming out of industry, and for every chip you need something called as compilers for that specific chips, so that these high level languages are converted back to the binary code. Here is our CPU. CPU understands only ones and zeros. Return something. Okay. So this is our high level language. Okay, something like that. Okay. So we'll see that in a demo in a while. So when you try to write a program in, say, on an Intel chip, and then you compile it, you get a binary code, something like a.out, or it can be any file name, of course. File name doesn't matter. So you can execute it. That means you can, after compilation, that means you convert the program that is readable by humans to binary code. So this is done by compilers. So compilers have different stages. We will see now. Above compilers is to convert high level languages to assembly level language, and then convert it into binary code. So when we try to do this, the problem is still the high level languages can be written anywhere, and it needs to be compiled for a specific hardware. That means when you try to compile your program on, say, on an Intel chip, so you might have got an executable, something like a.exe, and then you copy this exe file and then try to put on, say, on a Motorola chip or an AMD chip. So this won't work. That is because, as we saw earlier, the binary code that is interpreted by Intel chip is very different from Motorola chip or the AMD chip. So Intel chip could be reading data from um, right to left, and Motorola could be reading it from left to right, and their opcodes could be different. So it could be move xy, that means move x to y. So some other chips might interpret as move xy as move y to x, something like that. So there are several um, challenges here. That means the programs that we have written and compiled is very hardware specific. So either you need to have a cross compiler to compile the program to the target device, that means target hardware, or you need to copy paste the high level language that is written here, high level language program, say test.c, and then take it to the PC where the Motorola chip is present, and then you try to compile it, if it has a compiler, to compile it to that, and then you get a a.exe, and now you can execute that program. So this is the challenge. So that is why the languages like C, C++, they there are several cross compilers to compile programs from one system to another system. The challenge here is, say for example, your company is using a certain language and it wants to change its hardware. The problem is that you cannot simply copy paste the software that is written, say for example a Microsoft Word. So you cannot copy paste the executable of MS Word, such as like excel.exe, to another system directly. You need to have the source code of excel.exe. Maybe it has millions of lines of code, and then it needs to be compiled to a target hardware. So the base hardware supports only this excel.exe, and in order to execute that on target hardware, you need to recompile it and generate excel.exe for this specific hardware. So that is the main challenge here. So in order to get out of this challenge, so there are also several operating systems that came up. So these operating systems, their job is to manage the resources. That means it has a RAM, computer has a RAM, it might have a hard disk, it might have a keyboard, it might have a monitor, and many peripheral devices like this, and of course it has a CPU. So when you install Microsoft Windows on your system, it tries to install the executables or the programs that are compiled for that particular computer or that particular CPU. So if you have ThinkPad, HP ThinkPad, so when you try to install Windows on ThinkPad, so it specifically tries to put the binaries that are supported by ThinkPad chip. The same thing you cannot install directly on say some other laptop, say produced by Apple, such as Mac or whatever it is. So when you try to install on top Windows on top of different hardware, you require different set of executables. So operating systems tries to manage the hardware resources, and it helps us to spawn the process, and it helps us to do the process management. The problem that we are facing now is that the program that is written in hardware 1 cannot be transported. That means the executable cannot be transported to hardware 2. That is because the binary code is not readable or not understandable by this particular different hardware. So in order to do that, you can take this source code and you can recompile it on this particular hardware. So if you take the source code and compile it here, and then you get a new test.exe or executable, which is a binary code that is read by CPU. So now these text.exes are completely different. There is a lot of difference between these two test.exes, but there is no difference in at the source code level. That is because the compiler takes care of converting one format to another format. So here you could be using GCC with certain options to compile this program. Here you could be using a same compiler with different options to say that okay, compile this for this particular hardware. So either you can compile it on any other device, it is called cross compilation, that means you are compiling for a different hardware, or you can take the programs or the source code to the target hardware and you can compile it there as well. Right. So that is the challenge here. In order to come out of this challenge, so the idea that programming languages like Java, Python, PHP, these have an idea which solves this problem. That means they have something called as a virtual machine. When you install Java, you might have observed that it installs JRE, Java Runtime Environment. Similarly, Python has its own runtime environment, so it is called as interpreter. So when you try to install Python, it asks which version do you want. That means if you want for 32-bit and or 64-bit, or else it can also automatically detect your architecture, your computer's architecture, and it installs the right virtual machine. So the programmers who write this virtual machine make sure that your operating system is abstracted. That means you don't have to worry about the operating system or the hardware. So hardware is here. So you have hardware layer, and then you have operating system, where operating system does the job of managing the resources and managing the program execution. So that is what operating system does, and on top of this we have virtual machine. So this abstracts the calls or the executions that are required to be executed by a specific hardware. So the typical process is that you write a program in these languages such as Python, say for example test.py, and then you try to execute it. So the Python interpreter goes through it line by line, and then interpreter line by line and tries to map it to the machine code that is run by CPU. So interpreter does the job of doing this. So here for a simple program, Python can directly convert this into a bytecode, and then the bytecode is then mapped to the machine code. So the bytecode is nothing but the intermediary code that is consumed by the interpreter. So the process is that you have a source file, and that source file is converted to bytecode, and then this bytecode is read line by line, something like this, and it is then translated to its corresponding machine code instructions. So this is how now you can easily generate the bytecode, something like test.pyc. In Java, it is Java class files, test.class file. So that is the bytecode. So that bytecode can be copy pasted to another new hardware. So the virtual machines or the interpreters solve the problem of portability. Now you don't have to recompile the whole thing. Okay, so far we have learned how the code is converted into assembly code, and then it is again converted to machine code that which CPU understands. So let us get on to terminal and try to see how these things work and how do we convert from high level language to the language that the CPU understands. Okay. So let me get into the terminal mode. Let me open a test file and let me write a simple C program. This does absolutely nothing. It simply returns 0. So let me just add some instructions. Int count is equal to 0 and count is equal to count plus 1. So this is a very simple program, and I do not want to print it right now. So let me just simply compile it. So there is a compiler called as GCC which converts this test.c into an executable. So that executable is nothing but a.out that you are seeing here. So if I try to see that file, so it looks gibberish and it is not human readable format. That is because it is simply a dump of binary code that is generated out of compiler. So if you try to execute it, so it doesn't print anything, so it just executes and comes out of the program. So let me try to print something so that we have visual proof that it is getting executed. Printf. I've been used to Python for some time. Right, let me execute it. So it is printing. So whatever we are trying to print. So now let us try to see the stages of the compilation. So there is a option in GCC called save temps. It produces intermediary files that are done in compilation process. Test.i is first level of the compilation. Let us look at the content. So when we did hash include, so these are the things that got included, and then there is also test.s. This is the assembly level output. So this is the assembly code that is specific for this particular target machine. So these are the instructions, and this is again converted to a dot out. Since we cannot, it is gibberish. For example, I can try to open it. It looks gibberish, but we can try to see, or we can dump the binary content of it. So just by doing xsd. So this is the binary content of the executable. So this is exactly what CPU tries to read and then executes it. So for only few lines of code, so much of binary code is generated. So CPU, what it does is, once this code is loaded onto the RAM, so these are the code. So let us take one line for now. So once this is consider or imagine that this is a RAM. This is the RAM, and the data is stored in sequential manner. That means in address 0, and this is stored, and address 1, location 2, like, and address nth location. Okay, so CPU tries to pick up instructions line by line, and then it tries to decode the binary information that is present here. So this might mean an opcode, and this might mean certain the data that is read and operated on top of it. So this might, if you try to deassemble or disassemble it, or try to convert it back to assembly, that is reverse engineering, it might map to something like move x to y, or some add xy, something like that. So this is exactly the piece of binary stream that the CPU reads and executes it. Okay, so as I told you before, this cannot be copied and pasted onto a different machine and execute it. So what you can do is, you can take the source code. This source code can be transported to another computer, or you can specifically tell which machine or which architecture of the hardware you want to compile it for. So that is called as cross compilation, and you can do it like this. So you can as well, you can try to compile it to a different architecture. That means this is one of the hardwares, AMD FAM10, some hardware. So you can cross compile this test.c into amd.exe. So I'm just storing it in the executable as amd.exe. By default it stores as a.out. So if you look at amd.exe, so this is slightly different than the a.out. If you try to see the binary difference, it will be there will be a lot of difference. So let us try to see, let's try to execute this once more. Without the option. So let me just save this .s, that is the assembly code of this particular architecture, to test .s, and let me try to cross compile it for this particular architecture. MR just stands for the target architecture that you need to cross compile, and then you can do this. So now we have a new executable which is a lot different than the a.out that is for that specific architecture. So let us try to see the difference in between the assembly code of these two hardwares. Test.amd.s. Okay, so let me just vim diff test.amd.s and test.current.s. So you can see that the assembly code looks slightly different from each other. So this is for AMD and this is for the current architecture. So even the assembly level, since the assembly level code is specific for specific hardwares, so they differ. So that is the reason that you cannot simply copy paste a.out or amd.exe to any machine that doesn't support the execution. So these are the steps. So let us try to understand how the Python or the let us try to understand how higher level languages such as Python and Java works. So let me write a simple Python program. And let me try to execute this. So it just prints 1 because we have just incremented count to 1. So if you can, if you see the if you try to see the output, there is no executable that is produced by this program. So that is because Python has Python does not create bytecode unless it is imported as a module. All right. So in fact, we can override that behavior and we can try to generate the bytecode, and let's see how it looks. So if you look at this, so it has created a folder called as pycache, followed and beginning by double underscore. Let us get into this folder, and then if you try to read this particular so this looks gibberish. That is because this pyc file is nothing but the bytecode that we discussed. So in fact, you can dump this into binary format and see what is the content of it. So this is the content of the bytecode, and this bytecode is what the interpreter picks up. So imagine that this is in the interpreter domain. So this is an interpreter. So this will be put in RAM, and then interpreter reads it line by line. So this might mean beginning of the program and count is equal to 0. So you're just maybe the machine code could be something like slightly different than this. That is because interpreter does the translation from the bytecode to the machine code. So that is how the languages like Python and Java helps us to port the programs from one computer to another computer without recompiling. That means I can simply copy paste this program into my Windows machine or even some other uh, some other computer which has a different CPU, even to the Mac. The only thing that you need to make sure that is that the Python interpreter or the Java interpreter, if it's Java program, is installed on that target machine. So that is all that you need to do. So it helps us to solve the portability issue. Okay, so that is all I had for this lesson. So this is the process of how the higher level languages are converted to the machine code, and there are several problems because developers cannot remember, or it is difficult to debug the code in written in binary. So we have automated that into assembly level instructions, and then since assembly level instructions are quite specific for the hardware, now it can be automated to higher level languages such as C, C++, and things like that. So that's all I had. Thank you. Hope you learned something today. Thank you.